Okay, so we're going to find the double integral of this function right here for the region R and integrate it over A. So let's define R. R is an area on the xy plane where x is greater than 0 and less than 1, and y is greater than -2 and less than 2. So let's go ahead and graph what that looks like. So x's bounds are 0, so x equals 0 is just the y-axis, so right here, this line. And then x equals 1 is the upper bound. Great. Now for our y is bounded by y equals 2, which is this nice line right here, y equals 2, right? X equals 1, x equals 0. And then y equals -2 is down here, of course. Okay, now our region that's bounded by all of these bounds is going to be this rectangle that's right here inside, right? Okay, we're going to call that R, right? Because that's what it's called right here. Now we're going to write our integral based off of all of this. So let's go ahead and get our double integral signs, and then we have our function, which is just this function that we have right here. Just going to grab that and throw it right here. And instead of dA, we need to do what? We need to do dx dy, or dy dx. Okay, so let's just do dx dy. It actually doesn't matter, and I'll tell you why it doesn't matter. So this outer, whichever variable that we choose to do on the outside, y or x, the bounds have to be described in a way that they're not a function of any of the inside variables. So the bounds for y cannot be a function of x. Okay, well, the bounds for y are just 2 and -2. Those aren't functions of x, so it doesn't matter. But also in this case, if we just put x on the outside, then it wouldn't matter either because they're not functions of y. So whichever order you do it in, it won't matter. You won't have to change around any of these equations that you already have. That's not to say that it would be impossible to do if this weren't the case, but it's very easy in this case to just do it in whichever order. So we're going to do dx dy. So x goes from 0 to 1, and y goes from -2 to 2. Alright, so let's grab this nice new area down here all by itself. Okay, so the way we're going to do this is we're going to do the first integral, and then we're going to do the second integral, right? We're going to do each one with respect to its variable, right? So our first integration in this whole area right here is going to be done with respect to x, and then our second integration of whatever we get out of this is going to be done with respect to y. Okay, so let's work on our first integral. So for this, we're going to use U substitution, but before we even do that, what can we pull out of this integral? Well, we can pull out constants that the whole thing is multiplied and just pull it out to the front of the integral. So let's rewrite the integral. 3y squared are our constants, right? Because y we're going to treat as a constant. And then we have our integral just like before, except on the inside, now we just have x over x squared plus 1 dx. Okay, that's a little bit more manageable. But how would you integrate this? Well, maybe you wouldn't know exactly where to start, but let's go ahead and do U substitution. Let's call the bottom part, because that's the more complicated part, let's call that U. Okay, U equals x squared plus 1. Then du is what we need to find next. So we're just going to take the derivative, actually, of this, which gives us 2x plus 0, right? Derivative of 1 is 0. And dx. Don't forget to add that dx, that's important, right? And now we do substitution. Well, what are we substituting? Well, we're substituting, obviously, this for u, right? We already have that equality. But we're also going to substitute the dx. So we need to set this equation equal to dx and figure that out. So this ends up going to dx equals du divided by 2x. All right. So let's go ahead and plug all that in. Then we get 3y 0, 2. Okay, wait, but are my bounds still going to be the same? Actually, no, they won't be the same. This is a step that you have to remember when you're writing these bounds. You plug the bounds into your function for u, right? So 0 squared plus 1 is 1. 1 squared plus 1 is 2. Okay, great. We got that out of the way. That was the confusing part. The rest of it's easy. So x over u, right? Because we substituted this whole part for u. Well, we're going to substitute dx for this. So du over 2x. Great. Okay, so if we had any x's left over here, that would be a problem because we're doing integration with respect to u, not with respect to x. So our goal of doing U substitution is to get rid of all of the x's. And lucky for us, they both cancel out in this case, leaving us with 3y squared, and on the inside we have 1 over 2u, actually, du. Okay, now I'm pretty sure we know how to integrate this. This is just 1 over u times 1/2. And 1 over u integrates to the natural log of u. So all this is equal to 3y squared times 1/2 times natural log of u. And then we can go ahead and substitute our values for 1 and 2 in. So that looks like this. I don't know why my tablet's bugging out on me, but okay, so 1 and 2. Great. So let's go ahead and plug that all in and figure out what that comes out to. So 3y squared, because in this case we're still working on dx, right? All of everything here is still just this part. So we're still working on dx, so we're not going to plug anything in for y yet. Okay, so 3y squared times 1/2 times natural log of, let's see, well, natural log of 2, right, minus whatever's on the bottom, so we have natural log of 1. Okay. So maybe that was a little bit confusing what I just did there and how I wrote that out. Well, let's go back and do it out manually the way that you should do it. So we do ln2, right? Because that's our upper bound. And we subtract it by whatever we get from the function when we plug in the lower bound. So this was from plugging in the upper bound minus whatever we get from plugging in the lower bound. 3y squared times 1/2 times ln1. But wait, we can just factor here, right? We can pull out this whole part, right? We can pull out this whole part to the outside. And that's what ends up giving us 3y squared times 1/2 ln2 minus ln1. Okay, and after a while you'll become comfortable enough that you won't even have to do this first step. You can just jump straight to doing this. All right, and then we simplify from there, and what do we get? We get 3/2y squared natural log of one thing minus the natural log of another thing is equal to natural log of the first thing divided by the second thing. I guess I should write that out more formally. ln x. This is just a general equation that I'm writing. This is not specific to what we're doing right now. ln x minus ln y is equal to ln x over y. In case you didn't know. Okay. Great. So, of course, 2/1 is just 2. So that's what we have. Now, let's go to our next step. So now we're going to plug in for, we're going to do the second integral with respect to dy. So let's go ahead and start this down here. So what was that? Yeah, from -2 to 2. So we're going to go -2 to 2 of 3/2y squared ln2 dy. Okay, let's integrate this. It's actually pretty easy because everything in here is constant except for y squared. So we can just go 3/2, and then y squared integral of that is y cubed times 1/3, right? And then ln2. Okay, so then from that we have our 3's cancel out, right? And then we end up with 1/2 y cubed times ln of 2. Oh, and don't forget that this goes from 2 to -2. Okay, so let's substitute in 2 and -2 like we did before. So we have 1/2 2 cubed ln2. That's for our upper bound, right? Minus plugging in our lower bound, we get 1/2 -2 cubed ln2. All right, well, we can go ahead and simplify this by factoring to the same way that we did it before. We had 1/2 ln squared times 2 cubed minus -2 cubed, right? And that comes out to 1/2 ln squared times 8 minus -8, which is just 8 plus 8, which is 16. So we have 1/2 of 16, which comes out to 8 ln 2. All right, so just to go over what we did here from the beginning, we started by, we were given an equation and said that we had a double integral of that equation over a region with respect to that area. So now we have a region here. Well, we were given the bounds of the region, so we went ahead and graphed it just to get an idea of what it looked like. Okay, then after we had that, we used our bounds to set up our double integral. Then from there, once we had our double integral, we pulled out our constants for the first integration, which included y, because y is a constant when integrating for x. And then with this, we recognized that we needed to use U substitution. We defined u, we defined du. We used our definition of du to define dx. Then we used u and dx and substituted them into the original. And we made sure that we plugged our lower and upper bounds into our equation for u, right? For x, so we plugged 0 in for x, and we plugged 1 in for x. And then those were our new lower and upper bounds, right? Then, after we got all of our U substitution done, then we took our integral, right? And over our new bounds, we substituted those bounds in to the equation and subtracted the upper bound from, or sorry, the lower bound, subtracted the lower bound from the upper bound. And then that gave us this new equation here. And then we went back up to the top. Sorry for all this moving around, but we went back up to the top and we looked at our second integral, so from -2 to 2 with respect to y. We went and plugged in the result that we got here. Plugged in this result that we got here into that, which gave us this right here. And okay, well, we just solved again. We did the integration again. This time it wasn't as complicated. We didn't need to do U substitution because we just had y to the third power. Went through all of that, did our subtraction for upper and lower bounds, and all that gave us our answer, which was 8 ln 2, which can't be simplified further.